Hello guys, welcome back. So today we're going to start looking at double integrals, but this time over non-rectangular regions. One of the big indicators that you're going to be doing this is what I've already highlighted here in the problem is the fact that our bounds for our dy is actually in terms of a function of y equals x and y equals 1. So you'll see not numbers here, but you'll actually see some kind of functions. So before we actually start talking about how to solve this problem, let's get a general idea of what this is actually representing. So when we're looking at our bounds right here, and since it's in terms of y, we're looking at the equation of y equals x, and then that's the upper bound, and the lower bound will be y equals 1. So I'm going to, over here, graph what that looks like. There's our x and y axes. And so the line y equals x is here. And then the line y equals 1 is here. And then we're going to go over here to our change of x and see, okay, well, we want to go from x equals 1 to x equals 2. So right here at x equals 1, the y value is also 1. And then when x equals 2, we get the line this. And so the region that we want is actually this little guy right here. Well, highlighter's a little big, but it's okay, you get the idea. So a little triangle. So that's basically what we're representing in this problem, right? So that's our region, is that we're actually integrating over this particular region right here, all right? So when we do the problem itself, it's very similar to what we did in our previous videos. We're still going to integrate from inside out. So we're going to start with 1 to 2, and then we're going to integrate this again with respect to y, right? So that means that all of our x values are still constants. So I'm going to go ahead and integrate first of all by just saying that this is a number, so we just leave it alone. And we're going to integrate y to the negative 2, which is me y to the negative 1 over negative 1. And then we're going to integrate y 2y as y squared, right? Or 2y squared over 2, which becomes y squared. And we're going to evaluate this from 1 to x. So the only major difference here, friends, is the fact that instead of this being a constant like we did in the previous videos in lesson 16, we're actually now doing this where we're just going to plug in an x everywhere we see a y. Okay, so using the fundamental theorem of calculus, we're going to go ahead and plug in our x. One of the things that I'm going to do here is I'm going to pull the negative, and I'm going to do 2x squared, and then technically this will be over y, right? But since I'm going to replace y with x, I'm going to go ahead and put an x in for our function. All right, and then I'm going to do plus, again, the x is going to go in here. Everywhere I see a y, and then we're going to do the same thing with our 1. So we have a 2x squared, or excuse me, negative 2x squared, all over, again, 1, and then plus 1 squared. And then we're going to do dx. All right, so we're going to start simplifying this down. And so let's do a quick simplification. So we get x squared minus 2x. So I just rewrote the x squared over here and then minus 2x right there. Minus, actually let's put parentheses around this guy, even though we don't really technically need them. So we'll do 1 minus 2x squared dx. And then one more last quick simplification for this. We get from 1 to 2, and then we combine all our terms. We're going to get 3x squared minus 2x minus 1 dx. And then this becomes such a wonderful, beautiful problem for us to do. We're going to just integrate this again like we've been doing back in calculus A, B, and BC. We're going to integrate again. We get x cubed minus x squared minus x, all evaluated from 1 to 2. And so when we do our quick little plugging in, our final answers will be 8, right? So 2 cubed is 8, minus 2 squared is 4, minus 2. Subtract from that, we get 1, minus 1, minus 1. And when all is said and done, we get an answer of 3. Okay? So hopefully that makes sense to you guys, and we're going to go ahead and look at another problem. So for example number 2, we're going to do the same thing, and just so you guys are aware, we again have a value here of x. So the picture of this one is going to be y equals 0, y equals x on the value of 1 and 2. So with a quick sketch, we can look at the region that we're actually going over. And important that we're doing this is because eventually we're going to have to figure out how to set things up based on regions themselves. So it's just nice to practice it because sometimes you're not going to be given this. You're actually going to be given the picture and you're going to figure out kind of like how our bounds are going to be. So it's just nice to kind of go ahead and just do the simpler ones now to make sure that we kind of understand what we're doing. So remember, this is y equals x and then y equals 0, right? And so y equals 0 is obviously going to be our x-axis. And then we're going to bound it from 0 to 1. So 0 to 1. So again, it's going to be this region. Let me actually try to make my highlight a little bit smaller there. Okay, so there's our little triangle. Oh, I don't know why I did that, but all right, we're good to go. All right, so the rest of the problem just becomes the integration that we've done before. So this is actually pretty straightforward. So we're looking at cosine of x squared, and what's amazing about this, guys, is the fact that we are evaluating with respect to y, so this is just actually a number, and this is actually cosine of x squared. It's kind of hard to see that the theta is actually x squared. So we're going to go ahead and do cosine of x squared, which is just a constant. So when we integrate a constant to a variable y, we just get a y, so it's pretty awesome. And we're going to evaluate this from 0 to x. And then we're going to start plugging in, right? So everywhere we see a y, we're going to go ahead and plug in for x. So we're going to get x cosine of x squared. And then when I plug in 0 for this, oh, I forgot to do one more quick thing. So let me actually, notation here, guys, sorry. Forgot the dx. So when we plug in, we get x for y, and then 0, this whole constant. So this is technically going to be minus 0, right? When I plug in 0 for y, the whole thing goes away, and then with respect to x. All right, so how do we solve the problem? Well, good old u substitution here on out. So we're going to go ahead and make that u is equal to x squared. Our du is going to be equal to 2x dx, which means that we're going to pull out a 1/2. And we're going to go ahead and just go ahead and pull out the 1/2 right there. And then remembering that, guys, just a quick friendly reminder that if you decide to change your bounds, if you're going to keep it in terms of u, then you want to change your bounds. And again, this is what I can call the bridge step. So when x is equal to 0, u is also going to be equal to 0. When x equals 1, then u will also equal to 1. So in this case, it didn't matter because they're going to be the same bounds. But we're left with cosine of u du. All right, so 1/2, 0 to 1, cosine u du. And then, like I said, the rest of the problem becomes pretty simple. We're going to integrate cosine of x, which just becomes positive sine. Well, integrating cosine of u, excuse me. That's just going to be sine of u. And we're going to evaluate it from 0 to 1. So our final answer here will be 1/2 sine of 1. It's okay to be sine of 1. We don't know what that value is, but we can just go ahead and just leave it. Minus sine of 0. And so when all is said and done here, our final answer is going to be 1/2 sine of 1 minus sine of 0, which is just 0. So we get 1/2 sine of 1. All right. So hopefully that makes sense to you guys. And I think this will be a good stopping point for the first video where we just see very basic double integrals over non-rectangular regions. So in the next video, we'll do some a little bit more complicated problems. So I will see you guys in the next video.